Hi, everyone. Thank you for joining. This hopefully will be a bit of a fun talk. The title is a little provocative, how to build megaservices, and I'll give you what my definition of megaservices is in a bit. But really it's about building microservices that can handle ever-growing volumes of traffic and processing. So what I want to do though to start is jump into a demo application that I've been playing with. It's kind of my pandemic application, I guess. It's been a lot of fun to build, and it's kept me occupied, maybe sane during these times. So what it is though, it's a Akka Microservices demo application. And it's got an IoT, Internet of Things theme, and it's map-based. So let me flip over to the app itself. So this is the user interface to the application. It is a it's a map interface. It's on a live system. The demo here, I've played with it on different environments. This one's running in Amazon. I've also deployed it and done some testing and so on in Google as well, and also testing with it on local Kubernetes environments using Minikube, things like that. So the idea with this application is that it's trying to test the limits of Akka microservices, the cloud, databases, things like that. So with this application, it simulates an IoT type of an environment. Now, in further slides, I'll give you a little bit of an overview of how the application works. But in the user interface, you can see that there's markers distributed across the world. And these markers represent locations in the world where I've used this application to create simulated IoT devices. And in doing that, I'm trying to put a load on this system. So if I mouse around the world, it's showing me, for example, that up in the New York area, there's around 10,700 IoT devices that I've created. And these IoT devices they're not real devices, but it's data that goes into the system. And they're in a specific geographic region on the map. And what I can do is zoom in and show. So with this application, you can create devices and you can delete devices, but you can also change the state of devices, and the devices have a simple state. Either they're happy, green, or they're sad, red. And on the map, you can see, it's a little small, but it shows me that there's around, looks like 8,700 happy devices and around 2,000 sad devices. And it just goes like that. And I can mouse around different regions in the world, and it's showing me, the number of devices as I go into those different regions. Now, the data that I'm, of course, showing here is coming from the backend microservice system. So what I can do, though, is using, this very much like Google Maps. I can zoom into a part of the world. I'm going to zoom into the London area. And as I zoom in, what we start to see, the markers go away, and we start to see regions on the map where I've created devices. So these highlighted green regions, or maybe some red, or in between a little bit of yellow, they're showing areas on the map where I've created some devices. The way this map works, and I learned this as I was implementing this application, was every time you zoom a level in, the area is decreased by a factor of 4. So at this resolution, or at this zoom level, each region on the map here can contain, the way I've written this app, it can contain 4096 devices. If I zoom in one more level, now each region is 1024. And if I zoom in another level, it's 256, and then 64, 16, 4, and then 1. This is as low as I can go on the map, where I've got devices, like one device per region here. And the idea is that you can zoom around and you can place devices on the map. So I'm kind of at the edge of an area here where I've created some devices. So the way this works is that there's up in the, there's information up on the screen here. So in the top left, or I'm sorry, the top right, when I zoomed in, there's a little kind of menu or helper list here that shows me that I can increase or decrease the rate of device operations that I can submit using capital R or lowercase r. And then C for create, D for delete, H for happy, and S for sad. So what does that mean? So if I'm zoomed in all the way down to where there's one device per region, if I type a C and move my mouse around, then in that, wherever I click, it's going to create one device. So if I click, say, right here, the request is submitted to the backend system, and then one device is created. But, you know, so what, right? That's a big deal. I created one device. If I zoom out, though, up on the top left, what you see is there's a zoom level. So I went from zoom 1, now I zoomed out to zoom 3, and that shows a device density, which is 16. And then also shows the latitude and longitude. Now in the bottom left, there's devices in view. So in the area of the map that I'm looking at on the screen here, there's around 900 devices. And then on the bottom right, it's showing that worldwide, there's around 217,000 devices. So here now, if I type a C to do a create, it's going to create 16 devices. So I click that. So what happens is the request goes into one backend microservice. It does some work and it sends gRPC requests over to another microservice. It does some work. And then once all that's done, the data that I'm seeing here is kind of the end result of the full cycle here. So it's 16 devices were created. But again, still that's kind of boring. Let me zoom out some more. So I'm zoomed out to 256. If I type a C now and hit create, and then I'll zoom in and we can watch a little bit, what we should see is 256 devices get created. So it, you know, it's getting it all done. It does submit it at a rate. It's it's 1,000 per second, and there is some, again, there's some processing going on. So there's some eventual consistency processing latency involved in here. But where it really gets fun is when you start to zoom out even more. So I'm zoomed out to 1,000, and if I type a C, and I'll click, and if you look at this little region, it's saying 1 second because I'm going to create 1,000 devices. It's going to, but the rate is set to 1 second. If I decrease the rate, say to 500 per second by just typing an R, lowercase r, now the rate is 2 seconds. So if I click here, it's going to submit a single HTTP request, which cascades into a bunch of individual, actually gRPC requests coming from one microservice to another microservice. So that created 1,000 devices. And now things are getting a little bit more interesting, right? I just put a load. It's like over the course of 2 seconds, it was like, say 1,000 users hit the buy button if this was a shopping cart app. What I'm simulating here is over the course of 2 seconds, it's like 1,000 IoT devices came online and made themselves known to this backend system. So the idea is you can just keep zooming out and creating more and more devices. So I'm going to save this, doing that for later. But in a way, I can generate a lot of load with this app, and this is what I was really looking for. Like, for example, I'm zoomed out where the device density, every region in this grid would contain 65,000 devices. So if I click this, it would create 65,000 devices, and it would take around, the submittal process would take about 2 minutes and 11 seconds at that rate. I'm not going to do it right now, but that's the idea, that I can kind of very quickly generate some load and see how the system behaves. So this has been a really fun app. Also, this is a demo app that's available on GitHub, including all the JavaScript that makes this work. So if you're interested, you can grab these. It's a couple projects. It's just Java, Maven, Akka projects. They do use some backend databases, so it's, it does take a little bit to set up. But the idea is that I wanted to be able to make this available to you guys, so you could, if you were interested, you could play with this. So what's going on? I mean, the idea is, I kind of was playing with the term service. Microservice has been such a big deal for us for at least the last 5 or more years. It's kind of the mainstay in a way. A lot of people are building microservice systems, or they want to build it, or they built a couple different generations of service systems, and we've been learning a lot about it. But now I just kind of wanted to take the focus away from the scope of the code to the level of performance that we're looking for these services. So with this, what I'm kind of saying, that the definition here is a megaservice is a microservice capable of processing millions of logical operations per second. So the prefix is really about performance. So playing with this, just a naming convention, there's, say, deca-services or hecto-services or kilo-services. And I think for a lot of us, the applications that we're building or have been building and building today fall into this, hecto or kilo service range. That I think it's very, very common to build different applications and services that can handle hundreds of operations per second, logical operations per second. And many of you, I think, are starting to get into bigger, higher throughput applications where you're probably already into the kiloservice range. But very few, if any, really, except for the really massive ones like Amazon and Google and so on, Facebook, are in the megaservice area. And of course, there are some, but it's not the norm yet. So what's a logical operation? Well, it's pretty obvious, I think. It's things like with an IoT system, it's IoT devices are reporting some kind of telemetry information to the backend system that's interesting to the backend system, like creating a device or deleting a device, devices coming online or getting turned off, or also state changes of those devices. The classic shopping cart type of an application. A logical operation is things that we do as humans when we interact with a shopping cart, like add an item to a cart and so on. So on the back end, though, a logical operation can involve one or more service operations. And each service operation most likely will involve database operations. Or you may have operations where one service talks to another service, external service operations. And this is where the time really starts to get consumed is, some services are compute bound, but I think the vast majority of services are spend most of their time doing database operations or talking to external services. So in this demo application, it's composed of 2 microservices, and I call this demo is called Where on Earth, so WOE. So there's a simulator Akka microservice, and that service is really just kind of generating or simulating the outside world. So when I created a bunch of devices, the request initially went into the simulator service, like a single HTTP request went into the simulator service, but that guy took it and then did some fun stuff in Akka on the simulator service. And then when I said create 1,000 devices, what the simulator service did was then it sent 1,000 gRPC requests over to this twin service. And I call it a twin because I love the term. Some folks at Tesla are doing some really cool stuff with Akka and IoT, and they use the term digital twin, and I just love that term. So I use that when I named this Where on Earth twin microservice. So the twin microservice is a simulation of a real microservice. It's receiving telemetry requests from for creating or manipulating IoT devices. Also, just going back to this map, and I'll zoom out, all these, there's 200,000, 216 almost, or 200, yeah, 218, almost 220,000 devices worldwide, a lot, you know, on this map. The way the system works, there's every minute, telemetry messages come from the simulator service into the twin service. Now, it's just a ping. It's just saying, hey, I'm alive, but nothing really interesting's happened, so it doesn't trigger any kind of database operations. But all that traffic's happening. So that's around 3,000 or more gRPC messages per second that are being sent routinely right now in this application. So I'm trying to put some hurt, you know, on this system. So this is the composition of this demo application, these two microservices. These two microservices run in a cluster, and they run in Kubernetes. And Kubernetes is like the ideal orchestration environment for Akka clusters. So it really gives us, you know, a reactive type of a system. And the idea with reactive, I think fundamentally, is that you have services that are elastic. You've probably been hearing about this all day if you've been sitting in all the different talks. So this is certainly the case with this service. Both of these microservices are built as Akka microservices, which means they run in Akka clusters, which means they can scale up or down. And it's just lovely when it's running in an environment like Kubernetes. So both the simulator service and the twin service can scale up or down. And we get that resiliency as well. If we lose one of the nodes in the cluster, you know, say a Kubernetes pod dies for some reason, it's no big deal. This is just part of what Akka does. You know, it just recovers from it. And also there's this beautiful symbiotic relationship between Akka and Kubernetes. You lose a pod, Akka goes, oh, okay, I know how to deal with that. And it's handling things at the actor level inside of all the running JVMs inside of an Akka cluster. In the meantime, Kubernetes sees this issue, you know, that a pod's gone away, and it says, oh, you know, this service wants n number of pods running. One of them went away. I'm going to start a new one, and it brings it back. The other thing that this service does, and this gets back to the performance, is it uses CQRS, Command Query Responsibility Segregation, and not CRUD. So there's the whole read side and the write side. And the reason for this is for performance. If you're not familiar with CQRS, then here's a quick introduction. I'm not going to go into a lot of detail on it, but I think this, you know, it's fairly simple to understand. The idea is that, you know, say you have a client on the right that is sending in requests, and that the types of requests, or, you know, things that it's asking a service to do is either commands, which are, you know, requests to do something which typically results in some kind of a state change, or there's query requests. You know, I want to read some data. So with a command, the idea is that the request comes in, and the command is processed as an intent to perform some operation or do some work that hasn't been done yet, and that goes to what's called the write side. And the idea is that commands come in, they're validated by the service. If everything looks good, what's emitted are events. And events are historical facts. They're just things that have happened. And those things get put into an event store. And then those events then are propagated over to the read side. And these are two separate databases. So it's not a single database transaction where an event goes in and I'm updating, say, the query side. The idea is that you're decoupling these two things. And there's an eventual consistency gap between the two. So events are going in to the right side, and eventually they're propagated over to the query side for future queries that may need to be performed. So the idea is that you're not, say, you're removing some of the work that is typically done in, say, a CRUD type of an operation, and only doing a minimal amount of work to get the data in, to get it persisted without say, having the user wait for all the other work to get done. So the reason for this is really like I said, is for performance. You want to, CQRS is part of, I think, is the idea for doing this is you're decreasing the overhead on the database so that you can increase throughput. And it's done by trying to decrease some of the contention. I think another big advantage of CQRS, though, is I call it optimize the data models, but it's the flexibility of the read side. The read side is really designed for queries, and you're not having to deal, or you're not dealing with the constant trade-offs between, am I optimizing for writes or am I optimizing for reads? And it's always a trade-off. Like with a relational, you add indexes to optimize for reads, but that comes at a cost for writes. You budget your indexes to optimize your writes, but that comes at a cost for your reads. With Akka, also, it works out really nicely because there's the idea of statefulness versus stateless. And I like to actually refer to it as hot state versus cold state. So the idea is, stateless, the stateless pattern of the stateless ways of building an application is tried and true. Many of us, this is the way we do things, and it's great. It's there's no problem with it. I'm not saying it's a bad way to do things at all, but what you're doing though is that there is state, and the idea is that the state's cold. It's always stored in the database. So when you want to change the state, you got to retrieve the state from cold storage into hot storage, make your changes, and then put it back into cold storage and throw everything away. The idea with a hot state is that you get the state in memory and you keep it there as long as possible. And this is what actors do really well, which is Akka. So that's another optimization that comes with CQRS and hot state types of applications, is you're trying to reduce some of the contention on the database. You're trying to reduce some of the IO operations that you have to do to get work done, which means that you can get more throughput through the system. So with this demo application, both of these microservices have a right side journal where events are stored. And the twin service has what's called a projection or a view. And this is where the read side for queries. And those queries are really important for the way this application works, because on the map, the data that we're looking at here that it says, well, there's 16,000 devices. Well, that's coming from queries that are being performed by this user interface against the read side. And also, when I created some devices, when we saw devices appear in the map, it was that the request initially went into the simulator service. That did some persisting of events to the its journal. And there was one event at least for every device that was created. And then all those gRPC requests went from the simulator service over to the twin service. That persisted a bunch of events in its journal. And then all those events were then processed into the projection. So when I clicked and created a bunch of devices on the map, and we saw that stuff appear on the map, what we were seeing was the whole gauntlet here. I clicked, a bunch of processing happened here, a bunch of data was written to this journal, gRPC messages went over to this other service, a bunch of data was written to this journal. All those events were then processed by event handlers are called into the projection. And when we saw things appear in the map, that's what we were seeing was data that had finally arrived in the map. So in the read side, so the delay wasn't that bad. There was a lot of work getting done there. So just to kind of show that again, I'll zoom in to let's go. I think I'll just go almost anywhere in the map around this area, and just for fun, we're at 4,000. I'm going to set the rate up to 1,000. And I'm going to hit create here. So it should say, it says about 4 seconds. And so that's what's happening. Right now, the request went into the simulator service, did a bunch of writes in that service. The gRPC message went across. all the data then was propagated into the view, and we're done. So 4,000 devices. So 4,000 gRPC messages, 4,000 at least events were created in those two tables, and then there was a bunch of aggregation that was done into the view table, which is a little non-trivial, and it all happened there. So that's what we're watching in this demo app. So it's kind of showing, trying to help build systems that go fast. So to kind of wrap up, how fast is fast enough? Well, to prepare these slides, I did a little bit of digging, and a couple things that popped up real easy was I saw an article about Amazon does around $10,000 in orders per second right now. This year when everybody's buying online and lots of people buying from Amazon, 10,000 orders per second. And I did just a little guess some math, and I said, all right, say there's an average order size of $50, so that's 200 orders per second. That's not too bad. And another thing I did was, say you have an IoT system with 1 million devices, and every one of those devices sends in a telemetry message to the backend cloud system once a minute. And every 10 minutes, something interesting happens that's worthy of getting recorded in a database. So that's around 1,600 or so devices. But this one's fun, and it's actually today. 11/11 is a big, huge shopping day, the biggest shopping day, I think, in the world. In China, it's called Singles Day. And just saw an article today. They started shopping back in the beginning of November. So I guess when they opened up on November 1st, in the first 111 minutes, Alibaba did $1.5 billion in orders. $1.5 billion in just under 2 hours. So anyways, did a little bit of math on that one, say $25 per average order. And if my math is right, you can check me on this, but that's still like 9,000 orders per second. That's a lot. That's a lot of money. That's a lot of traffic. So, how fast is fast enough? I think that we're in the kind of deca-service range these days. But this decade has gotten off to a real fun start. And I think for us, though, it's in the IT business, especially for those of us building back-end cloud systems, it's just going to get more and more interesting. Just for fun, I grabbed these pictures, from walking to riding animals to, driving in vehicles to flying in the air, rockets, and who knows what's next is coming. But I think for us, that it's going to be writing applications that consume more and more data and process more and more data. And I think all of us are going to be getting into these bigger and bigger areas. So this is an area that we're focused on with Akka, and things like CQRS, and trying to explore building ever bigger systems. A lot of our customers, a lot of people using Akka and Lightbend technology are doing some pretty serious stuff, and that's where we want to be. But I think that's where a lot of you guys are going to be going as well, if you're not already there. And if you're already there, it's just going to, I think, just keep growing, because we have this insatiable thirst for data. So the two projects, here's the links for these two GitHub projects. And it's just under my account in GitHub, McKee H3, and it's WOE, where on earth -sim, and WE, where on earth -twin. As always, well, maybe not with everybody, certainly for me, I'm always procrastinating on the documentation. I do have READMEs in these things. I definitely want to polish them up. Because I've been trying to document the process for deploying to Amazon with where this demo is running with Amazon Key Spaces for Cassandra and Amazon RDS for Postgres. I've been using other databases. I've also did some deployments for on Google and Minikube and so on. So I'm trying to clean up the mess in those READMEs. But I think if you're interested, you could do a deployment to Minikube if you have a reasonably beefy laptop or development system. So those two projects are there for you to take and including the map UI. The JavaScript is part of the project that I wrote as well, and that was a lot of fun using some very cool JavaScript libraries. So that's it. I would like to thank you and go into QA, and you can reach me, of course, at on Twitter or LinkedIn or just email me at Lightbend.
That was great. Thank you so much, Hugh. We are going to Q&A, so if you have any questions for Hugh, this is the time to ask them.
Oh, yeah, okay. If I understand the question, I think it's a great question. And the whole thing, the whole eventual consistency thing is that I think initially one of those hard pills to swallow for us, where because it's so different than the way, that we normally do things. We grew up, I know I did, on CRUD. And the lovely transactions that are supported, atomic transactions that are supported by backend databases and so on. The all or nothing deal with atomic transactions. It's either all the changes are done or they're not done. The idea is that having to wait, say, for things to happen can be tough. I think at first, because it's new. So I think if like the question, your reservation is not complete, we're still working on it. I think that can get interesting when you're actually designing, say, the behavior of your system, and you're kind of playing a game where you're trying to put off as much work as possible, but you don't want to annoy your customers. So I think like with Amazon, for example, they do everything possible to capture the order, but they do the minimal amount of work because they have to handle so many things at volume. So this is I think one of those ones where you need to kind of try a few ideas, work through some scenarios where eventual consistency, or not all the work is done at once, it's done in a series of steps, and play with the flow until maybe you have something that is optimal for the system, but not sacrificing, say, the user experience.